So let's take an example here. Spring with constant 15 newtons per meter has a mass 16 grams hung from it. It's displaced 3.5 centimeters from equilibrium and released. When is its kinetic energy? First, 3.5 millijoules. Well, we have an equation for our kinetic energy. Now, it's 1/2 K A squared sine squared omega t plus phi. It's displaced 3.5 centimeters from equilibrium and released, which means that t equals 0. It's at a maximum, which would be a 0 velocity, which would be a 0 kinetic energy. So that tells us phi, in this case, is going to be 0. I could write a 0. We know the amplitude. We know the spring constant. We need to find omega. We know for a spring, omega is square root k over m, so that's going to be square root of 15 over 0.016, and I'll just leave it as that for the moment. So at what time is its kinetic energy? First, 3.5 millijoules. We can just plug and chug now. Kinetic energy, 0.0035, 3.5 millijoules, and that's equal to 1/2 times 15 times amplitude squared. If I write this in joules, I do need to put my amplitude in centimeters. Sometimes when we're writing our equations, I've said it doesn't matter if you put it in centimeters or meters, but if you're doing anything with energy or whatever, it's better to use all SI units. Or I guess you could use centijoules and centimeters, and then they would cancel out. But that's a little bit trickier to think through. Then we have sine squared of omega, which is square root of 15 over 0.016 times time, and time is what we're trying to find. So from there we can plug and chug 0.0035 times 2 divided by 15 times 0.035 squared is equal to sine squared. Take a square root of that, so that's the sine. Take the inverse sine, and then divide by square root of 15 over 0.016. And so we get the time at which this first happens is about 0.0052 seconds. So pretty quickly it gets to that speed. What is the potential energy as a function of time? Well, we know U is 1/2 K A squared cosine squared of omega t. We've already found omega, so it's 1/2 15, A is 0.01, oops, I was looking at the 16, A is 3.5 centimeters, 0.035 meters. Right. If you get a question like this on the AP exam, they'll probably be clear about whether they want decimals or square roots. I'll go ahead and 0.5 times 15 times 0.035 squared, so that's 0.0091875 cosine squared of root 15 over 0.06, 15.81 times time. All right. Now, what is its speed when it is 2.1 centimeters from equilibrium? The way you might first think to do this is to plug in 2.1 into the position equation, x equals a cosine omega t, and then find time, and then plug it into the velocity equation. And you could do that, but there's an easier way to do that. We know that our mechanical energy is conserved. So when it's first released, we have all spring potential, and when it's 2.1 centimeters from equilibrium, we're going to have spring potential and kinetic energy. We can solve for that. Halves all go away, and then we have 15 times 0.035 squared equals 15 times 0.021 squared plus mass is 0.016 v final squared, and we can solve for the velocity. So just because we know these equations for position and velocity as a function of time, don't forget that we can still do conservation of energy without respect to time. We don't need to calculate the time always. Just running through that calculation gives me a speed of about 0.271 meters per second. And what is its total mechanical energy at t equals 3.5? Well, total mechanical energy is a constant. The total mechanical energy for a mass spring system is 1/2 k a squared. So we can just go ahead and calculate that. This kind of question would be trying to divert you from the fact that mechanical energy is not dependent on time, so you don't need to worry about time. 0.009. Oh, I already calculated that number. I forgot that I had already calculated that number up above. Yeah. All right. So, moving on to the pendulum. The potential energy for a pendulum is gravitational, so it's equal to mgh, and we figured out a while back what that h is equal to, and I'll just draw it down here real quick again. So we've got this is our angle theta, this is the length of the string, this is the length of the string. So if we draw a triangle, and we know this height is the difference between the full length and the leg of this right triangle by trigonometry. This side is L cosine theta, so then this change in height here is L minus L cosine theta is this height right here, so that is mgl times 1 minus cosine theta. I have never seen any situation where you use this equation and then plug in for theta. Where'd it go? I don't know where it is in the packet. I've never seen a situation where you use the energy equation and then plug in theta equals theta max times cosine omega t plus phi. It's just nasty because you've got a trig function inside of a trig function, so I wouldn't worry about that. For the kinetic energy of the pendulum, a simple pendulum, remember you can treat it as rotational or translational depending on what's convenient, whether you want angular velocity or linear velocity, or whether you're given one of those. So if you take this simple pendulum, the mass 3.5 grams is displaced 8.2 degrees from equilibrium and released. As it passes through equilibrium, its speed is that. What is the length of the pendulum? Well, we know that conservation of energy applies. Our initial energy is all potential, and then as it passes through equilibrium, all of that potential has been converted into kinetic. Notice mass cancels out, and then we can plug in numbers and calculate what the length of the pendulum is going to be. 1/2 0.17 squared, just plugging in all the numbers that are given, and then we can calculate those values. Divided by 9.8 times 1 minus cosine 8.2. I'm in degree mode. Yeah, that's a little bit confusing. So the length of the pendulum is about 0.144 meters. This is a little bit confusing because pendulum displacements are almost always given in degrees, but when you're plugging stuff into the various equations that we have for position or even for energy, you need to be in radian because these things are in radian. So yeah, be careful, because sometimes you have to be in degrees, sometimes you have to be in radian during this unit. What is the pendulum speed when it is 4.5 degrees from equilibrium? Well, it's the same kind of deal. Now we know the length of the pendulum, so initially we have mgl times 1 minus cosine theta naught, which is 8.2 degrees. Yep. And then we have an mgl times 1 minus cosine theta final, as well as a kinetic energy, masses cancel out, and we can plug in numbers. So here we have 9.8 times 0.144, use the stored value, 1 minus cosine of, what was that again, 8.2 degrees. It's not a bad idea to tack units on for yourself. Put degrees when it's degrees to remind you, you need to be in degree mode. And 9.8 times L times 1 minus cosine 4.5 degrees plus 1/2 b squared. So that's just another conservation of energy problem. I'll go ahead and run it through. 9.8. I stored that value as L. 9.8 times L times 1 minus cosine 8.2, parentheses, minus, you could factor that too, I guess, and the 1's going to cancel out, but I'm typing more things and thinking less here. So that's all of our energies put together, times 2, square root gets us our velocity. Our speed is about 0.142 meters per second. At what angle from equilibrium is its kinetic energy? 3.1 times 10 to the minus 5th joules. Well, we're just doing the same thing. mgl times 1 minus cosine theta naught is our total energy. And that's equal to mgl times 1 minus cosine theta final plus the kinetic energy. Since we're given what the kinetic energy is, I don't need to use 1/2 mv squared. I can just plug in the value for kinetic energy. In this case, I would have to use the mass because I'm just given the value for kinetic energy. So its mass is 3.5 grams. So 0.0035 times 9.8 times 0.144 times 1 minus cosine 8.2 equals 0.0035 times 9.8 times 0.144 times 1 minus cosine 8. Not 8.2, theta final, which is what we're trying to find, plus 3.1 times 10 to the minus 5th. There's our big long expression. We can punch that in and figure it out. 0.0035 times 9.8 times L. This time I am going to think we've got, oh yeah, we need to multiply this out separately, so never mind. I'm not going to think. And then we subtract off 3.1. I need another closed parentheses, 3.1 e negative 5. That's equal to this potential energy, 0.035 times 9.8 times L. Now we're left with 1 minus cosine theta, so minus 1 times negative 1. Cosine theta equals that, inverse cosine. And we get that our angle is about equal to 5.10 degrees. So when we're doing energy stuff with the mass spring system, sometimes we just use conservation of energy equations that we already knew, but sometimes we have to plug in the functions, the position and velocity as functions of time, depending on what the problem is doing, what it's asking. With the pendulum, you almost always just plug in conservation of energy. We usually don't use the equations for position and velocity as a function of time.